Friday. Today we are going to spend the time discussing ideal gas questions. We have one question to talk about, and in a little departure from what I normally do, the problem I'm going to do does have some content that comes out of today's lecture, because I want to spend all Monday talking about open systems. So it's very little. I think we can all go along with it pretty well. It's just a small thing about polytropic processes, which you already know. We just do applying them to ideal gas systems. So, any startup questions? Any questions before we get started here? This is a high water mark here. We have the most people here that we've had in quite some time. So, nothing better to do on a Friday but come to a thermo lecture, I guess. So there we go. All right, we're told we have air in a piston cylinder. It undergoes a power cycle. Okay, and we are given the following graph. In the pressure here, which is in bars, and we have specific volume here in meters cubed per kilogram. And we have 1 and 5 bars and 1 and 5 meters cubed per kilogram. And we go, here is state 1, here is state 2, here is state 3, and we're going this direction. Here we go, and we're told that this is isothermal. And the question is, what is the efficiency? And that's all we've given. That's all we're given for the whole thing. Air in a piston cylinder undergoes a power cycle. We're given a graph, which gives us some state data. We're asked, what is the efficiency? So as we get going further and further here, we're getting less and less, it seems like. But we can figure everything out we need from this information. Okay, and that's kind of where we need to make sure we are, that we can take the clues that are given to us in the problem statement and decipher those clues. So first thing, what is eta? The efficiency is going to be, what do we want? What we want is our net amount of work. What do we have to give? We have to give some Q in. That's not the only way to write this equation. We can do it equals 1 minus Q out all over Q in. That's another way to write that. So we're going to have to figure out what the Q outs and Q ins are here. So this goes back to the same type of problem we had on our first exam, where we're going to have to look at this, every process and the cycle and all those rules that apply. Okay, so what I'm going to do here is I'm going to say, okay, it's a cycle, so I know that the change internal energy 1 to 2 is equal to Q12 minus W12. I know that has to happen. I know the change in internal energy 2 to 3 is equal to Q23 minus W23. I know the change in internal energy from 3 to 1 is equal to Q31 minus W31. And I know that if I add all this together, I'm going to get 0 is equal to the summation of all the heat transfers minus the summation for all the work. Now note, there's a couple times that we've had this show up to us in the last, I've seen some people that said, okay, whenever I'm looking at a problem that's not a cycle, and they've said the heat transfer equals the work. Okay, so the main thing I want you to make sure is only the heat transfer equals the work when you're talking about the entirety of a cycle. Okay, in the top 3 equations, the 1, 2, 2, 3, 3, 1 equations, there are 2 things here that go to 0. Give me one of them. Work from 3 to 1 goes 0. It's correct. Why? No area under the curve. That's one way to say it. Or you can say it's a constant specific volume process. There's no boundary work. Absolutely. Work from 3 to 1. This goes to 0. What is another thing that goes to 0? One more thing. Keyword is isothermal. The heat from 1 to 2? I'm glad you said that. You're wrong, but I'm glad you said that. I waited at 8:30. They said that I had to say, Phil, I'm going to tell everybody else I planted that answer, okay? Because I wanted that to be the answer. Because it is wrong, but it is such a common answer. Isothermal, there's no change in temperature from 1 to 2, and so the question is, okay, then it must have no heat transfer. It can't change its heat if it has, if it can't, there should be no heat added if there is no change in temperature. But that is not true. You can keep the temperature the same. You're changing the state. The specific volume changes. Other things change. Remember, the one that you should know clearly is water. Water can change state from liquid to a gas without changing temperature. We're just dumping heat into it. Okay? So don't say that something is isothermal that's adiabatic. That's important. There are situations where isothermal and adiabatic go together, but not here. So thank you for answering the question like that, so I can talk about it for 3 minutes. But it's wrong. But still, isothermal does help us with something. Something goes to 0. What is it? The question is, internal energy 1 to 2 is the correct answer, and why? Because there's no change in temperature, and why? Okay, so that's what you've gone through all the whys. So the correct thing is that U2 minus U1 goes to 0. This goes to 0 because we're dealing with an ideal gas. And an ideal gas, the properties are only based upon the temperature. So I would look up the internal energy at 2 at the temperature, and the internal energy at 1 at the temperature, and they would be the same temperature, and so that would go to 0. Okay, that's what we need to understand. That goes to 0. Now we do have some work from 1 to 2, and we have some, so we're going to have some heat transfer from 1 to 2. That's a good discussion. I'm glad we had that discussion here this morning. Hopefully that will pay dividends in future homeworks and exams. Okay, now we have to solve this thing, and I told you that I will tell you if a problem is polytropic or not or whatever. I've said that I would say that. And I have told you if the problem is polytropic or not in this, but it's hidden. And the word is isothermal. And this is what we talked about in the lecture this morning, so if you've watched it already, this is going to be a little bit of a repeat. But let's talk about isothermal. We know it's an ideal gas. So let me write the ideal gas equation for state 1 and state 2. Okay? I know that pressure 1 times volume 1 is equal to mass 1 times R1 times T1. And I know that the pressure 2 times volume 2 is equal to the mass 2 times R2 and times T2. Okay, now in this situation, it's a closed system. It's a closed system, so mass 1 is equal to mass 2. No mass is leaving the boundary. We also know it's air, so the gas constant, R, is going to be the same, so I know that R1 is going to equal to R2. And I know from 1 to 2 it is isothermal, so I know that T1 is equal to T2. So that's telling me that MRT1 is equal to MRT2, which is equal to a constant. It's a constant number that's equal to. If they're the same thing, it's a constant. So really what this is telling us is that PV is equal to constant. So anytime in any problem that there's things that occur that you say it's an ideal gas and it is isothermal, that's telling you it's polytropic with N is equal to 1. Are we okay with that? That is something you can memorize. You can just memorize and say polytropic or ideal gas process, isothermal process between two states, it's always polytropic, n is equal to 1. You can memorize that, or if you forget, this is a little bit of a proof or the thing to get you out of the hole. Okay? So now that I know this, now I know that I can find the work from 1 to 2 because I have to start plugging away at these things and figuring out what the answers are. So the work from 1 to 2 is going to be the integral of PdV. But it's a special case here that we know because n is equal to 1. It's going to be equal to PV times the natural log of V2 all over V1. And I'm going to choose pressure volume 1. Doesn't really matter. Pressure, I could use pressure 2 volume 2 or pressure 1 volume 1. Doesn't really matter. Now I haven't been given any volumes in this problem. I haven't been given volumes. So I'm in a little bit of a quandary how I deal with this equation. And I could do it a couple ways. The first way I could say I'm just going to assume some mass. I'm going to just assume a mass of 1 kilogram or 2 kilograms or 75 kilograms. It doesn't really matter. Or what I could say is I'm going to do this. I'm going to solve for work 1, 2 is equal to mass times pressure 1, specific volume 1, natural log of specific volume 2 over specific volume 1. And then solve for work over mass. Because that's going to give me, that's going to be okay. Because if I look up here a moment and I look at our equations, if I divide everything by mass, the mass just kind of falls out. I don't have to worry about it. The efficiency of the cycle is going to be the same whether I'm dealing with 1 kilogram or 1,000 kilograms. Per mass, it's going to be fine. So that's what I'm going to do. I'm going to work on it like that. Okay. So I have to make sure all of my data is going to be in here with per unit mass. So I have to go through here and I'm going to divide everything in this equation by mass and go with it. Now I can solve this. Work 1, 2 all over mass is equal to pressure 1. I'm not going to keep referring back up there. You can see it in your notes. But pressure 1 is going to be equal to 5 bars. So I'm going to do 5 bars. I'm going to convert it and see here. I'm going to say times 10 squared kilonewtons per meter squared. I know that 5 bars is 500 kilopascals. Kilopascal is a kilonewton per meter squared. So I'm going through those units in my head. If you're not comfortable with that, do the conversion. Okay, I may be going a little fast. One of the feedbacks that was given to me on the survey, which by the way, please submit the survey, is I need to slow down a little bit on some things, and I know I am fast. I need to talk a little bit more about where I get things into these tables. I need to talk about conversions a little bit more, so I'm going to try to work on those things. The specific volume at 1 was given to us as 1 meter cubed per kilogram. We're taking it times the natural log, V2 over V1. They're going to cancel out the units there. It's going to be a 5 all over 1, both in meters cubed per kilogram. That falls away. I know my units here need to be in kilojoules per kilogram, and if I look at this, meters cancels here. I got kilonewton times meter over kilograms, which a kilonewton meter is a kilojoule. So I'll go ahead and just do that right here. 1 kilonewton times a meter is 1 kilojoule. And so I have kilojoules per kilogram, and I'm set. So now I'm going to go to my trusty calculator. I'm going to type all this in there and see what we can find. So I have 500 times 1, which is okay, times the natural log of 5. And I get that this is equal to 804.72 kilojoules per kilogram. And I want to make sure, does that make sense? From 1 to 2, and I go back up to my diagram. 1 to 2, I am expanding. I am going from a smaller specific volume to a bigger specific volume. Expanding means that my system is working on the surroundings, and my sign convention says that that is positive. And I'm getting a positive answer here, so I'm pretty comfortable with that. So now I have this work 1, 2. Whoops, that's not what I wanted to do. I have this work 1,2 over mass, and that's going to also tell me what this Q12 over mass is. So now I have that work 1,2 over mass is equal to Q12 over mass, which is equal to 804.72 kilojoules per kilogram. Okay, I'm going to go ahead and put a double underline over it because this is important. And now we're going to start, going out to the next equation. What can we find? What can we find? Everybody okay with this so far? Okay, the next one, we know from state 2 to state 3, it's constant pressure work, it's compression. Constant pressure compression work. So, work from 2 to 3 is going to be equal to the integral of PdV, constant pressure, so it's equal to pressure times V3 minus V2, or, because we're dealing with specific volumes, is equal to mass times pressure times specific volume 2 minus specific volume 3 minus specific volume 2. And we can find that work 2,3 over mass is equal to pressure times V3 minus V2. Very similar to what we had before. The pressure there is equal to 100 kilonewtons per meter squared. The specific volume at 3 is 1. The specific volume at 2 is 5. And this is going to be in meters cubed per kilogram. Again, we check our units to make sure they work out. We have kilonewton meters, which is a kilojoule per kilogram. And we're good to go. And this is pretty easy here. 1 minus 5 is 4. Negative 4. Negative 4 times 100 is going to be negative 400 kilojoules per kilogram. Okay, so I know that my work 2,3 over mass is equal to negative 400 kilojoules per kilogram. And that makes sense. It's negative. We are compressing. It should be less than what we had before because it's the area under that curve is much smaller. This, even though I'm not sure if the answer is correct, there's indications in the problem statement. I mean, in what I know that I'm comfortable. It's reasonable. Okay, if I got this number to be 4,000, I look at that above. I should say, no, that's not. There's something wrong here. There's something wrong here. Okay, so now up here in the previous problem, I now have, or previous segment here, I have this information. And I'm looking and I don't exactly know how to find Q23. And the internal energy from 2 to 3 requires that I know temperature information. And so I think, okay, then I'll go to the next problem down. And, well, the internal energy from 3 to 1 indicates I know temperature information. And I don't know how to find the heat transfer there, so I'm kind of stuck right now. Kind of stuck with what I need to do. And we often get this way. We get stuck. Where's that other information? What's that piece that we need to know? And with ideal gases, when you're dealing with an ideal gas, and only with ideal gases, what we're going to have to say is, let's see if we can do something with the ideal gas law. It's usually that key that gets us out the door. Okay? It's usually that key. So let's look at it, because we know that we have this equation. We have mass times U3 minus U2 is equal to Q23 minus W23. And I've already said that I'm going to find that U3 minus U2 is equal to Q23 over mass minus a minus 400 kilojoules per kilogram. I know that for ideal gases, U3 and U2 are a function of temperature and temperature alone. So if I can find the temperature of that state, I'm going to be okay. So how do I do that? Well, I do that by the following. I say that P3V3 is equal to M3R3T3. Look, it has temperature in it. That has temperature in it. So that's good. So let's see if we can solve for the temperature at 3. T3 is equal to P3V3 divided by mass 3 times R3. And here we have pressure 3 times specific volume 3 over the gas constant at 3. And we know each one of those pieces of information. So we can solve for our temperature at 3, and that makes us happy. So T3 is going to be equal to the pressure at 3, which is equal to 100 kilonewtons per meter squared, or 1 bar. And our specific volume at 3 is going to be equal to 5 meters cubed per kilogram. One. Thank you. 1 meter cubed per kilogram. Our R value that we're going to be dealing with is the R value for air. Going to be 8.314 divided by the molecular weight of air, 28.97, and the units here are going to be kilojoules per kilogram Kelvin. I've automatically taken out the kilomole by dividing it by the molecular weight. And we got to check our units to make sure that this is all working out here. So here we're going to have kilonewton meters, which is a kilojoule. Kilograms go away. We're going to have Kelvin, and that Kelvin is going to switch up here into the numerator when we do everything, and that's good. That's what we want. We want answers in Kelvin. So I'm going to type this into my calculator. 100 divided by 8.314 times 28.97 gives us a number that is 348.45 Kelvin. Now, T2. T2 is, we're also at a pressure 2, which is 100 kilonewtons per meter squared. But state 2, the specific volume at 2 is 5 meters cubed per kilogram. And then we're going to divide by 8.314 divided by 28.97 kilojoules per kilogram Kelvin. So if you can look at this, you want to save yourself some time in the calculations. You might have already seen this. The difference between T3 and T2 is a 5. So if I multiply my previous answer by 5, I get what my T2 is, 1,742.24 Kelvin. And now I had those two temperatures. So the ideal gas equation really helped us here. Okay, so this T3 is going to be at 348.45, and U2 is equal to 1742.24. Now, you look at those two numbers and you think there's not a chance in the world that we're going to find those exact temperatures in our tables. Okay, that'd be pretty unlikely unless you had a really, really exact table. So there's probably going to be interpolation involved. Okay? And this is why students really like constant specific heats over variable specific heats. So let's look at this. It's going to be U3 minus U2, right? Well, these are going to be two table values, or it's going to be C sub V times T3 minus T2. In this version, we're going to have two interpolations. In this equation here, we might just have to have one interpolation to find out what is the C sub V value, and that's it. So many times students really like constant specific heat because it just eliminates the amount of interpolation we have to do. So what I'm going to do here is I'm going to go over to the document camera, and I'm going to go to table A22 in our SI tables, table A22, and I'm going to get the ideal gas properties for air, table A22, tables in SI units. And I'm going to go look for my temperature here, and I'm going to say that, okay, 1742 is between these two numbers, so I'm going to have to interpolate between these two numbers to get my value. Now, I'm going to skip this step this morning. I'm going to give you what the value is. So I found that U2 is equal to 1,742.24 1,432.5 kilojoules per kilogram. And U3, from 348, well, that's going to be on the previous page. 348 is going to be between these two numbers, our internal energy between these two numbers, and we're going to get a value of 248.9 kilojoules per kilogram. Okay, so I should make a note here from interpolation. All right, now let's just say that you're in a situation on the test where you are in a time crunch, and I ask for interpolation like this. You know how I grade, or you've seen one example of how I grade. I like to give partial credit. I like to show if you know the material. I'm not going to let a single answer derail the whole rest of your problem. So if you don't have the time to interpolate, you have like 5 minutes left, but you want to show me that you know something, what I would do here is not interpolate. I would say, okay, I am going to go for 348. I'm going to get the value for 350, 250.02, write it down. When I go here over here for 1,742, it's closer to this number here, 1750. I'm going to use 1439.8. Write it down. Go with it. That's what I'm going to do on my exam, and I'm just going to move on. Now, you could make a note, running out of time, making some assumptions or getting closest values, and go on with it. That's what I would do. And I'm going to see that, recognize that. Maybe they're worth 2 points apiece, and you lose 4 points. It's better to lose 4 points than lose all the remaining points. Okay, so if you spend the time to do the interpolation, show me what you know. That's important, to show me what you know. That's what I'm here to help you understand, or help you. Here's what I'm trying to grade on, what you know. Okay, and you are under some time stress, so I understand that happens. Okay, so now with this information, now we have this equation. We have 248.9 minus 1,432.5 kilojoules per kilogram equals Q23 minus a minus 400 kilojoules per kilogram. Okay, and so we know that Q23 is going to be equal to what? 248.9 minus 1,432.5 minus 400. We get that value is equal to minus 1583.6 kilojoules per kilogram. And I want to just, when I get these, I want to make sure that I know what the sign is. The sign's negative. So that means that for heat transfer, the heat is leaving the system. Now, this brings up to a point that I want to talk about your homework that is assigned for today. I've been getting some students, and it's a good question. They're saying, Dr. Wanklyn, I've worked this problem over and over and over again, and I know the answer is correct, but I'm unsure why Wiley won't take the answer. Okay, and it's the problem that it's really similar to the problem I did here in class. In fact, it's the exact same problem I did here in class, except for in class I did a variable specific heat version of a constant specific heat problem. It's about that paddle wheel. And the problem statement says, Wiley asks, what is the value of the work done by the paddle wheel? Okay, you know when you calculate it that you should get for that paddle wheel, it's the surroundings acting on the system, you should get a negative number. Okay, surroundings are acting on the system. So you get your answer. Let's just say it's negative 10. You calculate it. Okay, it makes sense. I've done the check. It's logical that it's negative, everything like that. I type in negative 10. Wiley does not accept it. I go back and check my work. I look through it all over again. I'm certain I get negative 10 again. I'm certain that that's the answer. And you're right, it is the answer. Negative 10 is the answer. But the way that Wiley asked the question is it said to provide the magnitude or provide the amount of work done by the paddle wheel. When they say work done, they are already saying in the problem statement, we know it's negative. I want you to give me that the paddle wheel does 10 kilojoules of work. So they want you to give the magnitude. And so if you take away the negative and you put positive in there, it'll accept your answer. Okay, so that's happening on the homework that's due tonight. Okay, so I'm trying to stop myself from getting texts at my phone kind of blows up at 11:30. Become very popular at about 11:30. So hopefully that doesn't happen tonight. All right. So what do I have here? I have I figured out this information here, and I figured out this information here. Okay, all this left here, I don't need to find U31. That's not necessary in my problem, because my problem statement's only asking me for the summation of my work and my heat transfer in. So I need to figure out what my Q31 is. Okay, and so to do that, what I'm going to say is I know that the summation of all my heat transfers from the cycle is equal to the summation of the work for the cycle, which is equal to Q12 plus Q23 plus Q31 equals W12 plus W23 plus W31. Okay. So what did I find for Q12? I found that this is equal to 804.7 plus the heat transfer from 2 to 3 I find was minus 1583.6. I do not know what the Q31 is. That's my unknown. The work from 1 to 2 is 804.7. The work from 2 to 3 is equal to minus 400. And then we have 0 going on there. So the only unknown here is Q31. And so we can find that Q31. We can just cancel off this thing. 804s go away here. And we have negative 11583.6 plus 400. And we're going to get that Q31 is going to be equal to, I did that wrong. Yeah, I can do this. It's going to be 1,000, I did that right, 1,183.6 kilojoules per kilogram. Okay, I should make sure I get this up here. I was finding this per mass. I should be keeping my variables correct. Sometimes I just get kind of scratch paper-like when I'm working on things, and I want to make sure things are correct. So this is Q31. It means that we have 1,183.6 kilojoules of heat per every kilogram of air inside that piston. We're going to get 1,183.6. If I had 2 kilograms, I would double that. If I have 4 kilograms, I quadruple that. Okay, it's how many kilojoules per every kilogram of air. Think about it in words. You'll become a better person at thermodynamics and a better person overall. Your friends will like you more. It just will happen. Using units is going to change your life for the better. Okay. So now I've got everything I need to. Now I can go back here and find my efficiency, and I can say that's equal to the net work over mass over Qn over mass. My net work is going to be 804.7 minus 400 kilojoules per kilogram. And my heat transfer in is all the positive heat transfers that I have. I have 2 positive heat transfers, 1 negative heat transfer, so 2 are coming in and 1 are going out. So this is going to be 804.7 plus 1,183.6. And when I do that, that's the wrong answer. I did that the same thing this morning when in class. I forgot. I subtracted the top number and then I subtracted the bottom number, which is incorrect. 804.7 plus 1,183.6. And this gives me a number of 0.2035, or it's 20.35%. Okay, very interesting problem in that it deals with cycles, it deals with efficiency, it deals with first law, it deals with ideal gases, it deals with ideal gas laws, it deals with polytropic processes. It's just a beautiful problem that talks about a whole bunch of different things. Okay? And it gave us very, very little information. It gave us a diagram, a graph, and it gave us its air in a piston cylinder. And then we go through and decode what it's asking us to find. If you can have a conversation with a problem like this, if you can have a conversation with all of your homework like this, you're going to have more success on your homeworks and on your exams. That conversation needs to happen. If you have a situation where you don't know what the problem is saying, you can't speak with it, then we have to slow down and work on those kind of things. If you don't know how to find the properties, we need to slow down and figure out how to know those kind of things. There are going to be, we already have half the exam that's on October the 12th. We already have it in your pocket. Okay, there are going to be 2 closed system problems. I can give them to you next Monday. You're ready for them. There are going to be 2 open system problems. You'll be ready for those in a couple days. By the end of next week, you will have all the material for the exam, and then we're just going to keep practicing it. Okay? Of those 4 problems, 2 closed system, 2 open system, there's going to be 2 ideal gas problems in there. And one of them is going to be constant specific heat, and one of them is going to be variable specific heat. You just need to recognize these things. If you recognize it and put yourself in the right area, then you can start thinking about, well, okay, here's how I analyze it, here's what I go. That thought process is very important. Michael Jordan said that when he was playing basketball, the game slowed down for him. You know, the game slowed down for him. I know when you're in the middle of a test, and you have 2 hours on the clock, things can kind of ramp up with you. But if you can get it to slow down and say, okay, I know what this problem is saying to me, I just got to do it. Okay, I know what the next problem is saying to me, I just got to do it. I'm not sure on problem 3, but I do know problem 4, I'm pretty sure, so I'm going to go and do it. And get all those things done, and you might have 45 minutes remaining that you can concentrate on problem 3, and then you can just show me everything you know about that problem. Write out the governing equations, go through the steps, start writing through that, and then you can be successful. Okay, that's my goal here. That's my goal here. I'm not going to give you 4 regurgitated problems from homework or from an old exam. I'm just not. I want to see how you think. Okay. Any questions that you have for me? Okay, I don't have enough time to really do anything else today, but if you do have questions afterwards, I have the exam. If you turned in a physical copy of the exam, it's here for you to pick up. We'll be talking in this class about open systems starting on Monday. And don't forget this stuff. Keep in touch with this, because don't let it get rusty, because it's going to come back on the exam. But have a good weekend. Let's hopefully we have enough players to have a team this weekend, beat Oklahoma again. That was fun last year, and especially because the people beside me were big OU fans, and that just was wonderful. Just was a wonderful experience to have by all. So anyway, I will see you later. See you on Monday.